All right, beautiful. So again, I want to stress that what we're going to talk about in this second half here is entirely supplementary. This is something that's just for your interest, if you're keen on it. It's not at all anything I'm going to examine you on. This is just a way for us to think a little bit about our formal systems that we've developed and, yeah, kind of draw some connections about the way we've done it or the other ways we could have done it. So in order to get to what I really want to talk about, which is expressive adequacy, we're going to have to do a little detour. And our detour is going to be via some notions of substitution and defining what we'll call disjunctive normal form. It's going to be kind of weird, but hear me out. Notably, what we're going to talk about for the duration is we're going to focus entirely on TFF. And we'll think about how we could have restructured our language, truth functional logic, in other different ways. The thing to note first is that if we think about our natural deduction system, right, we have the De Morgan laws, the DEM rules, right? And these De Morgan laws highlight a really weird symmetrical link between disjunction and conjunction, which we can define this sort of way, right? A conjunction B is, and we'll treat this as sort of semantically equivalent to, right? This is just the double turnstile put both directions. Is semantically equivalent to this. And similarly, A or B is semantically equivalent to it not being the case. In effect, what you have is that whenever you had a disjunction, you could have replaced it with appropriately placed negated conjunctions. And the same thing too with conjunction, right? Whenever you had a conjunction, we could have used this structure instead. So this tells us something about the relationship between the connectives, conjunction and disjunction. They're what we call duals. Duality is the generalized notion of this. We can have just this be any n-place connective. And then we can define its dual, which will be this with a line underneath it, and the following way. And note, we've just sort of written this to allow for any number of atomic sentences to be involved or non-atomic sentences. Right? The dual operator attached to whatever string, that's going to be semantically equivalent to the original operator with negations appropriately placed. Note that this formula fits exactly what we had in the previous slide. This is kind of cool. Here's the other really neat thing. We can very quickly and easily prove that a dual of a dual is going to be our original operator. Basically proving, to go back a slide, right, that conjunction's dual is negation. Conjunction's dual is disjunction, disjunction's dual is conjunction, and if we thought about the dual of conjunction, we'd be right back to disjunction. You're never getting new operators, you're only just whopping back and forth between the two. So here's a very quick and dirty proof. It's a sketch, but you can sort of see the structure. If you start off just with the definition of what a dual would be, right, we can very quickly do what we'll call contraposition, which is where we add negations on both sides. So note this becomes double negated. This just takes the single negation. Then we can use the definition of negation to kind of distribute across. Then by double negation elimination, we can go from, right, the negations placed over here to no negations over here whatsoever. Then we can introduce our dualed dual, right? Note it's got the two lines underneath it now instead of just the one. And of course, that's going to be defined as what we have right there. So then by transitivity of equivalence, we're going to get the dual of a dual is the original operator we started with. It's a quick and dirty proof, but it's really lovely. Because what it shows is that you're not, if you think about duality, You're never gaining new operators. You're just bouncing back and forth between the two duals that you have, no matter how far up you want to go. So duality is a really interesting feature. And it's worth thinking about what are the duals of some of our connectives. We know what the duals of conjunction and disjunction are. They're duals of each other. It's very hard to think about what the other operators might be. But this already kind of gets us thinking, right? Note that if conjunction and disjunction are duals in this way, we technically don't need both of them. We could have gotten by with just one. That already suggests something interesting. How many connectives could we have used? What's the smallest number of connectives we could have had? The next thing I want to mention is this notion of a normal form. So normal forms are ways that we can manipulate or re-express TFL sentences. Normal form theorems are ways for us to effectively guarantee for any TFL sentence, there's guaranteed to be a tautologically equivalent one in some kind of normal form. And I'm going to give you two normal forms. Our first one, the one that's going to be helpful for us later on, is disjunctive normal form. So disjunctive normal form is a TFL sentence that satisfies these following three requirements. First, the only connectives in the sentences are negations, conjunctions, and disjunctions. And these are distributed in the sentence in a very particular way. Every occurrence of negation has minimal scope. What that means is that if there's a negation, it can only be attached to an atom. It cannot be attached to any complex part of the sentence. And secondly, no disjunction occurs within the scope of any conjunction. In other words, this sentence has the following structure. At the base level, there's atoms or negated atoms. Then those are conjoined together. And then those clusters of conjunctions are joined up by disjunctions. So you get a sentence that looks a bit like this. I've got the plus minus to indicate it could be negated or it might just be unnegated. So the negations are here. Then these ones are conjoined up. And then these clusters are disjoined up. Disjunctive normal form has this particular structure. Only those three connectives. Negations have minimal scope. Then the next level up are conjunctions. Then the next level up are disjunctions. Disjunctive normal form is kind of handy because you can put it to use in various places. So we can very quickly prove what we'll call the disjunctive normal form theorem. The DNF theorem says that for any TFL sentence, there's a tautologically equivalent sentence in disjunctive normal form. And I'll show you a recipe for generating it. Here's a sentence we'll use. Note that what we can do, we can produce a very quick truth table for this sentence and get out our matrix and when the sentence is true and false. So here's a recipe for generating a tautologically equivalent DNF sentence. Find the lines where the sentence that you're interested in is true. So right, we have here, 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 and here. What we can then do is build conjunctions out of the atoms that are required. So if the atom is true, the atomic sentence goes in. If on evaluation this sentence is false, then the negated atom goes in. So again, if we look at line 4, say our target sentence is true, A is true, B is false, and C is false. So that means we'll get A, conjunction, negation B, conjunction, negation C. We see this sort of process here. It's really straightforward. So for every line where our target sentence is true, we build one of these. And you can guess the next step. The next step is we take these and we put disjunctions in between them. And here's the really cool thing. By doing it this way, we guarantee the sentence we produced, this with disjunctions in between them, will be true when and only when our target sentence is true. So this, not really that scary of a sentence, long, but fairly straightforward, is guaranteed to be tautologically equivalent to our original target. And note, there's nothing specific about this target. You can do this with any TFL sentence. You build the table, you find the lines when it's true, go back a slide, you then use the matrix to tell you what parts go in here in your conjunctions, and then you disjoin up the conjunctions that you built. It's a neat little process, and it shows that for every TFL sentence, there's guaranteed to be a DNF sentence that's tautologically equivalent. Now we can also talk about conjunctive normal form. Conjunctive normal form, shockingly, is basically the same as DNF, just with one switch. So the only things that are in there are negations, disjunctions, and conjunctions. Negation has minimal scope, but this time we flipped the scope of the conjunctions and disjunctions. So it's a conjunction of a bunch of disjunctive elements. Note that we already kind of know this has to be the case, because since conjunction and disjunction are duals, if we can prove the DNF, then we could very easily prove the CNF. We just say, cool, just dual it up. Every time you had a disjunction, replace it with the associated conjunctions and negations, and vice versa. I just mentioned the CNF. I'm not going to talk about it again, but it's just handy to see. The DNF is the one that's really interesting. So, okay. Note that what we've already highlighted is that when we're thinking about TFL sentences, we know there's going to be lots of readily producible alternatives that are effectively equivalent, that are tautologically equivalent, which is the only thing that really matters for TFL. And note that no matter what operators feature, we can always get it back down to ones that have just negation, disjunction, and conjunction. Interesting. So this starts to lead us to a big question. How many connectives do you actually need? How many connectives would we actually need in order to have a fully expressively capable truth functional logic? Now, obviously, I taught you one with 5, right? We have negation, conjunction, disjunction, the conditional, and the biconditional. Well, we can already see one of those is very clearly redundant, because the biconditional is just the conditional conjoined, right? So clearly it's out. We could get away with 4. But of course we could do better than that. Because I've already told you that whenever you have a conjunction, you could replace it with a disjunction, and vice versa. So we're already starting to see that if we want TFL languages, or TFL-like languages that are expressively adequate, capable of getting anything truth functional logic can say, you don't need all 5 connectives. But let's try and firm this up. Let's say that some connectives are jointly expressively adequate, if and only if, for any possible truth function. So any possible truth functional connective, there's a scheme containing only those connectives which expresses that truth function. So you can kind of think about it this way. We're going to build a language that captures every possible truth functional connective. What are the ones we actually have to have? Do we need to have a new connective for every possible truth function? Or could we somehow recapture them using simpler ones? Or put another way, no truth functional line is going to be beyond the grasp of a jointly expressively adequate collection of truth functional connectives. And here's 3 trios. Interestingly, we could have done TFL with just negation and disjunction, with just negation and conjunction, or just negation, and the conditional. We could have actually done the whole language just with any of those two pair. It's not quite right. Any of those three pair. That was the phrase I was looking for. It's interesting to see why. So let's talk through quickly why. So let's take some arbitrary n-place connective star. Right? By the DNF theorem, or we could use the CNF, but I like the disjunctive one better. It's possible to generate a scheme using these connectives that's guaranteed to be tautologically equivalent to star's characteristic truth table. Here's how. Right? If it's negation and disjunction, right, we have a sentence featuring star. Cool. We build a truth table for it. We then use the DNF theorem to produce the sentence featuring just negations, conjunctions, and disjunctions. And then we use the fact that conjunction and disjunctions are duals to get rid of all the conjunctions. So you'd end up with a sentence that's guaranteed to be tautologically equivalent to whatever you started with, featuring only negations and disjunctions. The one for negation and conjunction is the exact same. Right? It's cool, we use DNF to produce this sentence featuring only negation, disjunction, conjunction, and then we get rid of all the disjunctions using duality. So that's pretty easy. We could have literally done all of our TFL stuff using just negation and conjunction, or just negation and disjunction. Finally, we could do it all with a conditional. We use DNF to get everything down to just the three. And then we use these two schemes to replace conjunctions and disjunctions. And then we touch down Jesus. We only have negations and conditionals. So that's kind of neat. That's kind of neat. And actually one of the things that's interesting, and why I thought this might be kind of fun for you guys to think about, is if you're thinking about, say, programming up a reasoning machine, you only want so many basic steps for it to do. It's one thing if you have to program in 5 different basic truth functional functions. It's so much easier if you just have 1 or 2, but I'm getting ahead of myself. So we've shown that you can get by with just 2. Right? We could have done it with negation and disjunction, negation and conjunction, negation and the conditional. Could we do it with just 1? Could we have gotten away with just 1 connective? Well, actually, yeah. But here's the problem. The problem, and the one that kind of is the commonality amongst all, is negation. Negation is an outlier amongst all the connectives. It's an outlier grammatically, in that it's the only one that only takes a single sentence. But it's also an outlier in the way that it delivers its truth values. Because if you think about all of our connectives, conjunction, disjunction, conditional, biconditional, the top line of the truth table, where we input only truths, all 4 of those output true. Right? If you input A and B that are true into a conjunction, you get a true. Into a disjunction, you get a true. Conditional, you get a true. Biconditional, you get a true. If you input truth into negation, you get a falsehood. It's distinct in that sense. Its top line is false. If you input truths, it outputs falsehood. And similarly, it's interesting in that its bottom line is also false. Now, this is also true of our other connectives, some of our other connectives, but not all of them. But that first one's really striking. So negation's going to be the hard one to capture. If we wanted to try and just use 1 connective, not just because of the grammatical issue, but more importantly, because it's truth functionally so different than all the other ones. So let me introduce you to two-place connectives. You might have heard of these before. So one of them, we have the up arrow. We'll call this the Sheffer stroke, or you've probably heard it called NAND. NAND is defined like so. It's false when both value inputs are true, and it's true every other time. So it's called NAND because it's not AND. Very simple. On the other side, we have Peirce's arrow, or it's sometimes called AMP-HEC, but nobody fucking calls it that. Right? Everybody calls it Peirce's arrow. It's the arrow pointing down, and it's interesting in that the only time it is true is when both values input are false. Every other time, it outputs falsity. So it's interesting, right? If this is NAND, if this is not AND, what is this? What is this the converse of? So if we think, right, this characteristic truth table is the exact opposite of disjunction. Disjunction is true, 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 false. So this is sort of kind of NOR. Not quite, but it's along those lines. So here's what's very cool. The Sheffer stroke and Peirce's arrow, we haven't introduced them, we haven't talked about them yet, but of course they're just yet more kind of two-place truth functional connectives. Here's the neat thing. They capture negation. They capture negation because remember what I said about how negation's characteristic truth table works. Negation was the only one of the five we learned initially where if you fed in true, it output false. So here's something really cool. The only two-place connectives that are expressively adequate by themselves are those two I've just introduced you to. NAND and Peirce's arrow. We could have done all of TFL with them. So first, let's show that nothing else would do. To show that nothing else would do, we can think about all of the possible two-place connectives we could have had. All possible truth-functional two-place connectives. There's not that many. There's only 16. Because it's any combination of input values and output values. So there's not that many at all. We already know a bunch of them. 4 of them we're very familiar with. Conjunction, disjunction, conditional, and the biconditional. Here's 4 more. I've just defined them. We have 1 star, 2 star, 3 star, 4 star. Note, we don't really care what they are. All we care about is their truth functionality, their characteristic tables. And here are 4 of them. Notably, we don't care how useful they would be in capturing English either. We're just thinking about what possible truth functional operations we could have. These 4, and the 4 that we're already familiar with, we obviously couldn't use them alone to capture everything. They're not expressively adequate on their own. And they're not expressively adequate on their own because none of them captures negation. Negation requires an F in the top line. None of them get negation. So those 8, cool, we are already halfway to touchdown Jesus. We're already Bon Jovi. So now we think about the second half. So we can think about another option. These 4. We call them 5 star, 6 star, 7 star, 8 star. Again, we don't really care what connectives they are, how well they capture anything in English. We're just thinking about the functions we could define. And none of these capture negation either. And none of these capture negation because negation gives us a true at the bottom. And these ones don't. So we know that these ones couldn't be expressively adequate on their own either. So if we take these 8 and the 4 we started with, we don't have much left. We've got 4 left. And we can quickly knock out 2 more. We might think of, we'll call them 9 star and 10 star. These ones are ones that have, if you like, redundant positions. Their truth values are determined entirely by one particular element, say. And notably, these ones also don't capture all the things we want to do because there's lots of ones that they just simply can't. It's an easy one. Neither of these adequately expresses what we called 1 star earlier. And if we're interested in complete expressive adequacy, it has to be able to capture every truth function. So we're left with 2 tables. And that's the 2 we started with. The Sheffer stroke and Peirce's error. And it's a kind of fun proof here, because we literally just walk through every possible 2-place truth functional connective and have found that the only ones that could adequately capture negation, and the other ones too, are going to be these 2. So we get a very interesting kind of thing, right? If we want to capture negation, which is syntactically a 1 place, we just simply put the same sentence on both sides, and we have easy translation schemes. And if you want to do any of the other ones, for example, disjunction, here's how disjunction is going to look with the Sheffer stroke. Here's how conjunction is going to look with Peirce's arrow. You can kind of go from there, work backwards. So this is really, really interesting, because we theoretically could have done all of our truth functional logic entirely using either the NAND operator or Peirce's arrow. So here's a good question. Why didn't we? Why didn't we? Why didn't I teach you truth functional logic using NAND?
Because it doesn't capture anything we would care about in real life.
It does, though. Every time that we express something using the connectives we're okay with, we could have re-expressed it using NAND. But I think I get where you're going. Say some more.
It would require re-expressing those expressions, and it wouldn't sound very natural to us in English.
That's the big thing. Even if we could do it all using just NAND, look at how fucking hideous this is already. And this is just to say A or B. And whatever problems we might have with the TFL connections, this very quickly goes beyond comprehension, or easy comprehension, even for very simple symbolizations. So there's a really strong pragmatic motivation here. What's interesting, though, and this comes back to something deep and dark, and particularly relevant for you guys, is if we're thinking about computational systems, ones that don't have our pragmatic limits, something like this is really nice. The fact that we could recapture every single thing in truth functional logic with only one kind of function is really, really cool. But it is worth thinking about how the symbolization schemes go. Think about how difficult it would be to try and re-express everything using just these. We could, but it's notable, right, that there's something interesting about human limitations getting in the way here. I love this, though. I love the fact that there's theoretically just these 2 that could do it. But of course, what we haven't done yet is shown that they can. So let's very quickly show that they can recapture everything. It won't take long. First, we can show that NAND is expressively adequate by itself. Here's what we do. Take any TFL sentence you like, use the DNF theorem to produce a sentence using only negation, conjunction, and disjunction. We can then use our duality to replace all conjunctions with only negations and disjunctions. And then finally, to go back a slide, we can use this one right here to convert it into just nands. And it's going to be real ugly real fast. But we can do it. So that's how we could show that it's guaranteed, that NAND is guaranteed to be expressively adequate by itself. And you can kind of figure the proof for Peirce's arrow is very similar. In fact, you can see it's just changing one very simple thing, right? We use DNF to produce sentence using only negation, conjunction, disjunction. We then replace all the disjunctions with negations and conjunctions. And then we use, to go back 2 slides, we use this scheme, these 2 schemes, to get rid of all the conjunctions and negations. And there we go. Again, it's going to be a really ugly sentence, but you totally can do it. So the upshot is that actually when we think about how to capture something as simple and as powerful as truth functional logic, there's lots of different ways to carve that cake up. There's even some ways to do it with only just a single cut. And that's very striking. And it's interesting when we're thinking about whether the same holds true for FOL. Obviously, we could say the same things with regards to the truth functional connectors. But could we have done the same things with the quantifiers or with identity? That's when it gets a lot harder, a lot quicker. But it's still worth thinking about. So that's what I wanted to talk to you about. I think that's really fascinating stuff, getting very deeply into waters about the nature of formal logic and the nature of these formal languages that we've developed and we've talked about. So notably, to stress, the only part from today that's sort of immediately relevant is the material we talked about in the first section, properties of relations. Not going to ask you any exam questions on the stuff about expressive adequacy. I just think it's something that's really worth knowing about. What we're going to do for our next lecture is review. There's no more new material at all. So I'll have a very brief kind of section where I'll talk to you about the structure of the exam. We'll go through any kind of review questions, and then I'll have a little spiel at the very end about if you're at all interested in formal logic, some interesting things to think about going forward on your own time. But there's no reading. Just come with any extra questions you might have. For the tutorials this week, we'll work through this relations and expressive adequacy worksheet, as well as some additional FOL natural deduction, just to make sure everybody's on the same page. But before then, everybody take care of yourselves, and hopefully see you all Thursday and Friday. Thanks for coming, guys. I don't think that's deserving.